Welcome to NASA Edge.
An inside and outside look at all things NASA.
I gotta tell you, this is a great time for aeronautics because the X-Plane is coming back to NASA.
It's awesome.
We're being joined by David Richwine, who is the Deputy Project Manager for Technology for the Low Boom Flight Demonstration. How you doing, David?
I'm doing great, guys. How are you guys doing?
Awesome.
Are you excited too?
I am very excited. This is a great time for the project, and it's good to be here to talk to you guys today.
What is the Low Boom Flight Demonstration Project?
So NASA's done a lot of research over the last decades, really, in supersonic research, but the Low Boom Flight Demonstration is a kind of focused effort to work on the problem that we know is the most critical problem in supersonics, which is that low boom, or the boom that people have heard from fighters over the years and so on, that you don't want to hear that sound on the ground. And so we're working the overland supersonic flight problem. So we view that as the most challenging problem. So if we can solve that and then work the other technologies at the same time, we feel like that lays a path for overland supersonic flight in the future.
Which I have to say, for me personally, if I can reduce time in the air on a flight of any kind, how awesome is that?
Especially from East Coast to West Coast and back.
East Coast, West Coast, London,
Right.
Japan.
Yeah, so obviously the guy in the airplane wants to be half the time in the airplane, so that's certainly important too, but the other important part of that is the public on the ground and making sure they have the environmental or the boom or the noise that they hear on the ground. We want to make sure that's acceptable for the public as well.
You're taking on the unique challenge of pleasing everyone.
That's true. That's true. Very difficult, but that's the challenge that we have.
We're going to learn all different aspects of LBFD today, but I think to kind of kick things off, the main focus to get to the low boom is the design of the aircraft. And I had a chance to sit down with the Chief Engineer for LBFD, so let's check it out. We're here with Jay Brandon, Chief Engineer for the Low Boom Flight Demonstrator. How you doing, Jay?
Doing good.
So tell me, as Chief Engineer, what is your role in the project?
I'm kind of here to herd all the cats, so to speak, as we're developing the technologies that will be used for putting this airplane together. So, the NASA side will be developing a few subsystems ourselves, as well as putting all the requirements together for the airplane that then a contractor will actually build based on our requirements.
Speaking of that aircraft, looking at the preliminary design of the vehicle, it's unlike any design that I've seen before on the commercial side. Since the plane is going supersonic, you have to design that aircraft a little bit differently than, let's say, a Boeing 757, 737. What are some of the areas that you have to look for in designing a supersonic aircraft?
The key item is we want to have a low noise sonic boom. The sonic boom, of course, is the reason why supersonic flight over land is not allowed, because of the irritation of the noise to people and animals and such. So the design that you see reflects the technologies that are being developed to reduce that sonic boom. And the sonic boom happens because of a pressure wave that the airplane creates. And so when you go supersonic, you have a pressure increase in the beginning of the airplane at the shock wave, and then at the end you have the recovery of the pressure. So it's two sharp changes of pressure, and those happen very quickly. And what we're trying to do is design the airplane to slow down how quick that pressure change occurs, which then makes the noise that pressure difference generates less.
Now we're looking at these shock waves, so is that why you have to make the fuselage much longer than a typical commercial airliner?
Right, so it's in order to get that curve to be gentle, for the shock wave pressure distribution to be gentle. Normally it's an in wave, so it's real sharp increase, then a sharp recovery at the end. And what we want to do is round that out. So the change in pressure might be very similar, but it's going to occur over a longer period of time. So that's a function of the lift distribution and the volume and area of the airplane. And that kind of results in that long airplane, so you can spread all that stuff out and spread all the shock waves out so they don't coalesce into one sharp pressure spike at the beginning and end of the airplane.
And then also, looking at the wings of the aircraft, it doesn't seem like your typical traditional commercial airliner wings. It looks like it's more of a swept back approach.
So that high sweep wing is a traditional way to reduce the drag for supersonic airplanes. So most supersonic airplanes, you'll see that. They have a highly swept wing so that they don't generate all that drag. That's just a very common supersonic design feature to keep the drag down. So for us, the drag is not that important as long as we have enough power to overcome it. And we have a high thrust engine that we're using based on a fighter technology engine. So drag is secondary to us, but again, that volume and lift distribution is kind of the primary thing, assuming that we have enough power to overcome the drag.
So the whole purpose of LBFD is, it's not so much the final design of what's going to look like down the road, but you want to make sure that you can actually achieve low boom and then get that data that's needed for regulatory change to hopefully to change the rules of actually flying a supersonic vehicle over land.
That's right. So yeah, this will be a kind of a noise generator, and we'll be able to adjust how much noise we make with the boom by flying different types of profiles, and do a campaign over different places across the United States and get community response data, and then use that as a vehicle for regulatory change. And then the other thing is this will validate our tools of designing airplanes to adjust that sonic boom signature to get the lower perceived noise levels on an airplane. So at the end of this project, we'll have design methodology, that's validated by flight test, and you can apply that for new airplane design.
David, Jay did a great job talking about the design of the aircraft, and one of the questions I forgot to ask him is how practical is it going to be for a commercial supersonic aircraft to be that long and be able to move around airports?
Right, so the primary purpose of our project, the Low Boom Flight Demonstration Project, is really just looking at the overland supersonic flight and being a data generator for regulatory change. But there are challenges that the commercial airplanes will have to overtake as well and work. And we're also working those anywhere from the environmental concerns like noise and emissions at a high altitude and cost effectiveness and things like that. And so we're working those as well. And so again, while NASA's primary objective is the data part of this and for regulatory change, we're working the longer term challenges that have to do with the challenges that would enable commercial flight.
So say you fly the demonstration and it's completely successful and you meet all your objectives, and designers want to build those commercial craft. Will you guys provide all the data that you gathered for the design process and make that available to those designers?
Well, that's a great question. So that's one of the important parts that we took on when we did this experiment. We were saying, okay, our approach is going to be, while there might be some proprietary tools involved that we might want to protect, we really want the data to be open for everybody. So when we go fly these flights and do this atmospheric data collection and the community studies, we really want to make sure this data is available to all of our partners that are currently working these technologies so that they can make use of this data.
So it's safe to say that however long at some point when we have our first commercial supersonic aircraft at an airport, it may not look like our demonstrator.
Right. So the intent of the demonstrator really is to be not physically traceable to a commercial product, but we want the boom to be similar to that commercial product so that we're really just simulating the sonic boom and it's a sonic boom generator. And we have many other challenges that we want to make it a cost-effective solution. The commercial product would be a little more different.
Well, of course, once you get the design, there's also the element of simulation. Like, I didn't even realize that you had simulators for the low boom flight demonstrator at this point in the process that already begun. I had a chance to sit down with Tim Cox, who works with the LBFD simulator. Let's check it out. We're here at Armstrong Flight Research Center talking to Tim Cox, a control and dynamics engineer who works on the engineering simulator for the low boom flight demonstrator. Tim, the big question I have, because I normally think of simulators as learning to fly and the ability to fly cool planes, but in this case, this is an engineering simulator. Yeah. What exactly is an engineering simulator?
Part of it is to pilot training and things, but what we just finished now in terms of the low boom project is a preliminary design phase. And so in that preliminary design phase, there's a lot of design trade studies going on, it's a lot of iteration on the design. And so what you really want is a simulator that doesn't have to be too fancy in terms of what's in the cockpit and everything, but you want a simulator that has the best software models that go into it, so that way you can do these design trades. For example, with the control laws, which are basically the software that says when the pilot moves a stick, how the control surface is going to move. There's a lot to designing that. You want the control laws to make the airplane stable, and then you want them to provide good handling qualities or good dynamics so that the pilot can fly it easily and do what he needs to do with it.
So in that case, would you do things like if they said it's not as responsive as I need it to be as a pilot, then you would look at making that adjustment?
Yes. So one of the things that we've done in this study, last phase study, is that for example, we've put a couple of boxes on the runway, small boxes, and said, okay, and we bring the pilots in and say, now I want you to try to land inside those boxes. And so that's a challenging task for them. So they have to be in the loop trying to get the airplane to land, or touch down where he wants it to land. And the hope there is that as he does that, he will provide us comments back on whether it's easy for him to do, if it's hard, if it is hard, why, what kind of deficiencies are there in these control laws, so that way we can now go back and fix them before it gets too far down the process of the design process.
Now, do you ever do things like program little subroutines that say, don't put the landing gear down, just to tweak the pilot?
Oh, that's a good idea. We'll have to try to work that in.
I'm full of them.
Yeah. No, well, we do things like present with him potential failures or things like that, or perhaps give him gusts or kind of a difficult atmosphere to fly in, you might say, so that way he has to earn his money. If you make it too easy, it's no fun.
So this is an X-plane that we're talking about building, and since it doesn't exist, how are you actually testing in this simulator?
So one of the things that's been going on is that there's been a lot of data being collected on different models. So first of all, we take advantage of what's been done in the past. So we have a core simulation architecture that we use that has a lot of the fundamental stuff that's relevant to any airplane in it. We'll take, for example, a certain software model that goes into that sim. We can borrow it from a different airplane that's similar, but then as we go forward, we'll do tests and we'll update that model accordingly. So one of the big things that we look to is the aerodynamics. That's probably one of the models that has some of the most, I think, uncertainty on it. And so there's a lot of work done on computerized code that can tell us what they think the aero is. And we can do some wind tunnel tests to kind of support that. And we can incorporate that into an aerodynamics model and start to fold those into the sim. And that development process gets continually refined throughout this whole design phase. And as we go forward, it'll continue to be developed.
That's got to be one of the most unique features of developing an X-plane. You're literally going through this entire process from scratch.
Yes, it is quite a process, but there is a lot of tools available to help us in being able to develop these simulations. So the simulators at first will be maybe a little rough, but as we go along, they'll get better and better. They'll have more complexity to them, which will allow us to evaluate more and more different characteristics of the airplane and the pilot and the loop as well. And so that way, hopefully by the time it's ready to fly, we'll have a pretty decent sim that he can now go in and learn a lot of these characteristics before he gets in the airplane, which will help make it safer for him too.
So if you do your job perfectly, he'll get out of the plane after flying and say, no different than the simulator.
That's the goal. That's the goal, of course. We'll see how that works out.
So spoiler alert, Dave, I didn't actually get a chance to fly in the simulator when we were out at Armstrong.
You did?
Yeah.
It was cool.
Yeah, well, some of us did, some of us didn't. But what I'm wondering is, how about you? Have you had the opportunity? Is it a perk of the job? Do you get to fly in the simulator?
Well, I wouldn't call it a perk, but everybody, the engineering folks that are on the project get to fly the simulator, and we all kind of make comments. And so it's good for everybody to kind of understand what's the realism of the simulator. We're eventually trying to get that software and the hardware as realistic as we can get it to replicate the airplane. So, while that's not, I wouldn't call it a perk, it is certainly interesting because it helps you understand how the airplane handles in flight.
Did you provide any essential feedback that may help the development?
Well, I'm not as qualified as some of these guys like Tim that you talked to who really have a better feel for how the handling qualities of the airplane and how they would like it to behave in a high-speed and a low-speed environment, because that's really the trick here is the landing and the takeoff for an airplane like this is going to be much trickier. And so that kind of drives the need for additional simulation in that flight regime as well.
But you have flight experience in an F-15
I have
at
flown.
Armstrong.
In my younger days, I have flown.
So,
yes,
so you sort of have a good perspective of real supersonic flight as opposed to looking at this engineering simulator. Is there any similarities between the two?
Well, you certainly want the hardware very similar, so you have the same displays and things set up in the airplane. You know, supersonic flight in the back seat of a fighter is just the same as low-speed flight. You wouldn't know it when you're at high altitude. You don't really get that sensation of going that much faster. But I think the simulators are a valuable tool from a safety perspective and understanding how the airplane operates. So.
And that's a great point, because the lucky person who's going to be flying LBFD, Niels Larson, he's not going to be able to see ahead of him because he's going to be looking at a computer screen while he's flying.
Right.
And I had a chance to talk with Niels Larson at NASA Armstrong and see what's it going to be like to fly the LBFD. I tell you, this is a pretty awesome hangar. There's a lot of cool aircraft here. How long have you been flying for NASA?
Just over 11 years now.
And you have your favorite airplane in here?
Whatever I'm flying today.
You're going to be the chief pilot for the LBFD when it gets built?
Well, that's the plan right now, anyway.
You know, this is a different type of supersonic aircraft than, let's say, the F-18 or F-15. What are going to be some of the challenges that you're going to be facing when you fly this new aircraft?
Well, probably the biggest one we have is there's no forward field of view in the current design. It's almost like the Spirit of St. Louis when you look at it and, you know, there's a big fuel tank in the way. In this case, there's a big nose in the way. So we can't see forward, so we're going to have an external vision system, basically cameras and a screen to be able to look forward.
I mean, is that kind of nerve-wracking to not be able to see out the front when you're flying an aircraft?
Well, it's kind of funny because a lot of times you'll see we have some two-seaters, that's a single-seater behind us, but when you're in the back seat and you're an instructor, there's a lot of times you can't see out the front anyway because there's an ejection seat in front of you or somebody's big head in front of you. So you learn to fly without that.
I assume that you're going to have a lot of hours in the simulator before we actually take the LBFD up for its first flight?
Oh yeah, we'll have to have a lot of simulation both before the first flight and most likely as we continue to fly the airplane through the years. We want to keep the hours off the airplane so that it can be used for the research side and not so much for our proficiency. So we're hoping that the simulator can be pretty accurate so that we can get our landings down in the simulator so I don't have to burn all that time on the airplane.
Before we actually start collecting the data to make sure that the aircraft can actually achieve this low sonic boom when we get the data that we need, you're going to have to learn about the aircraft first, I'm assuming. Taking off, landing, getting used to the controls before we actually take data for low boom. Is that fair to say?
That's right. The first phase that we'll have is actually ringing out the airplane. The classic envelope expansion that you've always heard, pushing the envelope, going out and making sure that the airplane is safe to be flown in the envelope where we're going to need to go get the research.
And how long does that normally take to shake down an aircraft, make sure it's ready for flight?
Well, it really kind of depends on the complexity of the airplane. We're hoping that for low boom, that'll be somewhere around a year that we could do that. And hopefully there's not a whole lot of systems that are incredibly complex with the airplane, so we're pretty hopeful that that's realistic.
You're going to be relying on all your experiences in flying different aircraft, being a test pilot, being in the Air Force, to make sure that you're successful at flying this aircraft.
Yeah, that's right. I've flown about 100 different airplanes, some of them only once, and have different envelope expansion and airworthiness flight tests from my previous days in the Air Force and on exchange with the Navy. And here at Armstrong, we actually do some airworthiness certification kind of stuff every now and then. So we're pretty familiar with what has to go on, and we're just excited to get back to X-planes.
It is exciting. The fact that hopefully one day that business jets and even the commercial side, we can fly supersonic, over land, which would be pretty cool.
Oh yeah. I always give the example that around here it takes about 3.5 hours to drive to Vegas. And when I do some of the work in the F-15, it'll take me about, 20 minutes to fly over there, maybe a little bit more, turn around, and I get back in about 8.
Wow.
So, the kids really like that.
Picture this, you're on the LBFD, it's your first flight test, you're getting ready to take off. Are you gonna hear Chuck Yeager's voice in your head?
I've met him before. I don't know. We're both from West Virginia originally, so
the stars are lining up. You're making history.
Yeah, there's not a day you don't think about that when you look up at the skies around here. I mean, we have an X-1 sitting out in front of the center here. And, that was a purpose-designed airplane to go and break the sound barrier.
Right.
Now we're building a purpose-designed X-plane again to go and break the sound barrier again, to go faster, just like those original X-planes. But this time we're trying to go faster, but we're also trying to do it without producing too much of a boom, too much impact to everybody else. It's exciting because you're back there again. You're back to the early X-planes and some of that stuff. So, you know, it's going to be exciting. We're really looking forward to it.
You know, I thought I had a cool job at NASA, working for NASA Edge, but I tell you, Niels, he is going to be the man of the hour when he flies the LBFD.
As a pilot, that's like the Olympics. That's like the Super Bowl for getting an X-plane. I mean, flying an X-plane for a test pilot, that's the best job you can possibly get.
Well, you know, Nils and some of the other pilots that are working on the project have really done a great job. So the glamour part of this is flying the airplane, but really the pilots have gotten engaged in the design of the simulators, how the airplane should handle, safety features. So I think the pilots in this case have really gotten engaged in the design from the early stages. So it's not just the glamorous part where you guys think, oh, it's all about flying. There's a lot of other important stuff that they have contributed to the project at this point.
Well, I'm looking forward to seeing his feedback when he first flies a plane, how difficult it is to actually take off and land, not really seeing what's going on in front of you.
And I imagine that, as you said, Dave, being part of that design process, if you're going to fly this X-plane as a test pilot, you want to know everything about how it was designed and how it functions and how it operates, because the more you know, the safer you will be.
Yeah, so by the time he flies this external vision, he'll be very familiar with it. And so for him to say this is his first flight, it will be no impact to him at all. He'll completely, and even if the screen went out, he would be completely comfortable flying the airplane. So even in the failure modes that we anticipate, if they happen, it's all going to work out, and it'll be, you know, no problem for him.
Okay, David, so a lot of the preliminary testing is done, wind tunnel testing is done. Now we've gotten to the point where we actually can go and build an aircraft.
Right, and so it's a very exciting time. I mean, we've done all the concept studies, we've done a lot of the homework that we need to do, done a lot of the wind tunnel testing to look at these types of configurations and the flight controls and things we need to understand. And so we're really at the door to go build that demonstrator that we need to do this. So it's a very exciting time.
So over the next, 2 to 3 years, I mean, we're going to be in this phase of building and testing and flying this aircraft?
Right, so it takes roughly 2 or 3 years to detailed design and build a demonstrator, and then we expect the first flight in the next couple of years, and then we'll kind of go do the testing at that point, understand the atmospherics, and then work our way onto those community studies that are the ultimate goal of the project.
So is it safe to say by, I don't know, maybe within 10, 15 years that there could be people flying supersonic over land?
I think so. The regulatory process, like many governmental or regulatory process, moves a little slow sometimes, and it takes several paths to get that to happen. But I think they'll have the data in the next 5 or 6 years, and then we can make those regulatory changes, and that will help enable the kind of the commercial products to start coming to market, and really for industry to step up and make those products that we're all talking about, so that poor Blair can get to where he's going in half the amount of time.
Well, I was going to say, and in about half the time to get all the regulatory change, there should be an Xbox version of the LBFD that I can be flying.
Well,
in the
that might be where you fly, yes.
and you'll be flying it probably on an 8K television.
Thankfully. Let's hope, right? That would be perfect.
Hey, you're watching NASA Edge.
An inside and outside look at all things NASA.